All right, we are back. It's Mr. Sullivan. We're going to be on page 575 today. All right, we're doing lesson 2, Pert and Nert. These are two pretty famous formulas that we're going to use today, and we're going to talk about this natural base e. E is kind of like pi. It's a number. It actually has a value, but it's irrational, and therefore we use e instead of the actual like 3.14. It's short for pi, but it's not exactly pi. All right, down here, let's review real quick. Juno's opening her first savings account and deposits $100 into the bank. Great job, Juno. The bank offers 3% annual interest calculated at the end of the year. So she's making some money here. Not much, but she's making some. That's good. We want to write a function. All right, so I'm going to remember that her function, oh, that's a terrible pen. Her function is going to equal what she starts with, $100, right, times her interest rate. So she's making money, so that's 100% plus 3%. So that's 103%, which is 1.03. 1.03, we put that in. Now that is our function, all right? That is what I'm starting with, so I know that's t equals 0. All right, calculate after 1 year. Well, that's pretty easy. 103 to 1.03 to the first is 1.03. So this is going to be $103. Congratulations. So after 1 year, making big money. Let's see after 5 years. Let's put 5 years in. All right, so we have 100 and 1.03. Again, now this is just calculator work. You can put that whole thing into your calculator, and you should get $115.93. Now, just so we're clear, I want to make sure we all understand that this is why math is important. She did nothing. She made $15 in 5 years. Now, I know that this seems very small for you, but please understand that 3% is pretty low and $100 is very low. If you start that with more money, you are going to make more money. All right, that's one of the things I really want you to understand this about exponentials and sooner when we get into logarithmics. All right, let's go to the next page on 576. Now, I don't need you to go and cut out these things on 587. All right, but go to 587, and what you're going to see is you're going to see a bunch of graphs. And there's a bunch of formulas at the bottom. I just put them over the side here. What I want you to do is put these into your calculator, and I want you to figure out which graph goes with which graph. I want you to come up with some similarities and some differences, and see if you can't answer some of these questions down here. All right, what point do the graphs have in common, and compare the equations, what differentiates them. All right, so what is a growth and what is a decay? So I'm going to pause the video right here. You go ahead and do that on your calculator. All right, if you were to look here, you can see what I did. I matched them up. A couple of things I did was I would take it to the first power, because I know 2/3 of the first power is 2/3, or excuse me, 2/3 of the first power is 2/3. So I know, like, you go over 1 up 2/3. Now it's kind of hard to tell on here because it's not by ones, it's by twos. It's kind of wonky, I guess. So like over here, I know this is over 1 up 1.5, you know, somewhere in there. These dots are a little bit big, but I did know that, you know, the bigger this number is, the quicker it rises, right? 1 over up 3, 1 over up 10, right? Really quick. Likewise, I know this is really small, and I did also know this, that if I put it to the -1, so if I went back 1, that's like flipping it, so that actually -1 would go up 10, so -1 up 10 is like the mirror, right? The mirror image of that. So this one is like 1/3 to the -1 is like -1 comma 3, so that's how I got that one. All right, now if you look at all the decay ones, let's take a look here at all the decay ones. Decay, decay, decay. All those numbers are between 0 and 1. All right, all the b values are between 0 and 1. All right, and if you look at the growth values, growth, 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 all those are greater than 1. So if it's greater than 1, then it's going to be growth. If it's between 0 and 1, it's going to be decay. And when I look at the graph, I want you to understand, I understand that every decay goes down as I go to the right. But that's simply not a good enough explanation, because this then would be growth, right? It's going up. The thing that matters is looking at the gap here. The distance between my line and the asymptote, like that line right there, that 0, that is decaying, that's shrinking. Here, that gap is growing, so it's growth. The gap is growing, growth. Here, the gap here is shrinking, it's decay, all right? So let's talk about this. Analyze the growth and decay. What point do you have in common? Why? Well, I didn't point this out, but every time it had 0, 1. And why? Because there's no a value on this at all. There was none of them had an a value. That means anything to the 0 power equals 1. So it didn't matter what I had here, it equaled 1. So every point I had in there was 0, 1. All right. Compare equations of the 6 functions you sorted. What differentiates an exponential growth in it? We talked about that, right? So decay, this is really important. Are those values with the b that are 0 and 1, right? So again, let's remind ourselves that this is a general form of an exponential. A is our starting value, b is our common multiplier, our ratio. When our ratio is between 0 and 1, we have decay, and we have growth when that b value is greater than 1, right? And if it were exactly 1, we're not really moving anywhere, are we? All right, so that's how you know the difference between decay and growth, and we talked about it as a graph as well. All right, we're on page 578, all right? And we're gonna do a and b here. We want an exponential function now. I'm gonna just use it where I have no a value, just to keep it easy, right? Because there could be a lot of values that go through here, depending on the a and the b value combined, so let's just keep it like this. So it's increasing from negative infinity to infinity, and it goes through the point 1, 6. So that means when I put in a 1 here, all right, I'm going to get a value of 6 here. Well, what to the exponent of 1 equals 6? That would be 6. So that means my exponential would be 6 to the x power, because 6 to the first is 6. So when I plug in 1, I would get 6 out of there. All right, let's try this one. This is it's decreasing. Oh, decreasing. That means we know that b is going to be between 0 and 1, right? So it's probably going to be a fraction. All right, it says as I go negative 1, my point goes up 4. So my question is, when I plug, I'm going to get 4 when I put b to the negative 1 in. Well, if you think about this, negative flips something, right? So let's flip this. So this is now 1 over b. So what would I have to put in there to do that? Well, I would have to put in a 4 down here. So this is going to be 1/4. So y equals y equals 1/4 to the x. Because when I put a negative 1 here, it flips it and it becomes 4. So that would be our equation there. All right, let's go down here. We want to summarize the characteristics of these things. All right, so let's take a look. The basic exponential growth one. So that looks like this. And we're talking basic, no a value. So it goes through the 0.01 and it increases forever, right? So my domain, it goes from negative infinity to positive infinity. My range, there is an asymptote here, right? So that my lowest value here for my range is 0 to positive infinity, goes up forever. My asymptote is at y equals 0. My intercepts, well, I know it's never going to have an x-intercept. So let's make sure we know that. But my y-intercept is at what? 0, 1. Because when I plug in 0 for any of these, it equals 1, right? End behavior. So as x goes to negative infinity, what does y do? As x goes to the left, y approaches 0. As x goes to positive infinity, what does y do? Y goes to the moon, towards positive infinity. Intervals of increase or decrease, well, it's going to increase from negative infinity to infinity. All right, let's talk about a basic exponential decay. So we know we have this, and we know it's going to come down, and we know this point is 0, 1 again. I want you to pause the video and fill out the rest of this as much as you can all by yourself. There's going to be a lot of similarities, a few differences. Take a minute and do that on your own. All right, so if you notice, all of these are the same. The first one that's different is our end behavior, because as I go left, it actually goes high, and as I go to the right, it approaches 0. And then instead of increasing, it's actually decreasing, okay? All right, let's go to the next page over here on 579. Oh, we're back to Helen. Helen is opening her first savings account and is depositing $500 a year. All right, so this is one of those things you need to understand. Principal times rate to the times time, all right? So our principal is she starts with $500. Good for you, Helen. And what is her rate going to be? Well, her rate is going to be 100% plus whatever her interest rate is. Let me write that again. Her 100% plus whatever her rate is, or 1 plus her rate, all right? So her rate here says 6%, so 1 plus 0.06 for 5 years. So that's 500 times 1.06 for 5 years. And if you calculate that out, you should find that at the end of 5 years, it's $669.11. Now, it also wanted after 1 year, so we could do that. 500 times 1.06 to the 1 year would be $530. All right, so she obviously makes some more money. You'll notice that 6% is higher, 500 is higher, she makes some more money. Now let's talk about that. We're going to talk about this, compounding. Hopefully you've done this before. It's the same formula. P stands for principal, the money I start with. The K now stands for how many times something is compounded per year. All right, so let's figure out how much she actually would be compounded for per 6 months. All right, so her rate would be 1 plus her 6%, which is 0.06 over the number of times we compound it, right? So that's 1 plus 0.03. So for each 6 month period, she's only compounding it, she's getting 1.03, all right? Now that's like, why would I do that? I'm making less interest than 6%, right? But I'm gonna do this twice in 1 year, whereas opposed to this, I'm only doing it once per year. All right, let's take a little bit deeper look into that on the next page on 580. So let's write a function, savings account at the end of t years, compounded k times. So she had 500, all right, times 1 plus her rate was 6%, divided by k times kt, because k is the number of times I'm compounding it, and t is the number of years, right? All right, so now down here, we're actually going to do it. So let's do it for twice a year. So 500 times 1 plus 0.06 divided by 2 times 2, and it says 3 years, so times 3. So our formula is going to be 500, all right, 1 plus 0.03 to the 6. All right, I put that in my calculator, and I should have got 597.03. Now, let's be very clear about something. You guys are not great at putting stuff in the calculator, all right? No offense. But I can put this whole thing in my calculator one time. So I'm going to start with 500, parentheses, 1 plus, now I need to divide this. So I'm going to put in parentheses 0.06 divided by 2. All right, it was in the other parentheses, so now I have to put the whole thing into the 6, and I get 597, all right? But I needed both these parentheses, all right? All right, so I want you to do B, C, and take a look and see what you get for number 6. All right, so I'd put in 0.06 monthly, there's 12 months. Don't forget 12 up here. So I know that I'm dividing my interest rate by 12, which is making it smaller, but I'm also going to compound it 36 times, and it got $598.34. Same amount down here, I'm dividing it by 365, but I'm also multiplying it by much more, or I have an exponent much higher, and I get 598.60. Now, if you look at this, what happens when you compound it more often? Even though I'm dividing my interest rate, that exponent a lot more often actually means I make more money, and that's where they went down here. More money. All right, that's what we got down here. So let's take a look at that different way. All right, imagine that her bank offers her 100% interest. Wow, that's great. Complete the table to calculate how much Helen would accrue in 1 year for each period compounding when she starts with $1. So if you look here, yearly number of times I compounded was 1, put in the formula, and I get $2. All right. Down here, semi-annually means 2. Plug in instead of my K is really the only thing I'm changing here, right? Quarterly, that would be 4. So this would be 1 times 1 plus 1/4 to the 4 times 1. You can find that calculation. All right, I want you to do all this whole table. So let's think about this monthly. There'd be 12 months. Weekly, 52 weeks. Daily, 365 days. Hourly, well, that would be 365 days times 24, right? And I believe that gets you 8,760 hours in a year. That's crazy. Every minute, well, I'm going to multiply that by 60, right? So that gives me 525,600 minutes. That's insane. And then seconds, even more. Multiply that by 60, and let's see here, 3153600 31 million seconds. All right, so I want you to put those in the formula and see what you get. All right, you can see I stopped putting the formula in, but I did it here. Look at these values. They basically approach 2.718, right? I only rounded to 3 places to show that, right? But as this is getting closer, if you think about this, I could do it every whatever is after seconds, right? This is almost continuous, right? And that's what we talk about when we are compounding something continuously. So when we compound continuously, that would be the best, right? Because we know that the more we compound it, the more money we make. So when we compound continuously, you approach this 2.718 number. And that is E. All right, it's Euler's number. All right, he's the guy who discovered this. So let's take a look at our calculator. E, which is found right here in the blue, right down here. All right, E to the first is 2.718281828. Again, it's a irrational number. All right, it's not a pattern. It's not going to be 8281, 8281, 8218. Like we have this thing. All right, this is E. Okay, and this is what we can use whenever we compound in continuously. And when we do that, we have our own new formula. All right, our new formula is the amount after so many years equals Pert. The principal, what I start with, E, our rate as a decimal, I don't have to add 100 to it, and our time, Pert. Let's try out Pert. All right. All right, so on page 583, suppose Helen's investment of 500, that's our initial, compounded continuously, E, all right, at a rate of 6%, 0.06 times 1. We did find it for 1 year. And we also have to find it for 5 years. So that would be P, our principal. All right. Equals E times our rate, 0.06 times 5. We put those in our calculator, pause and see what you get. All right, so I got $530.92 and $674.93. Lesson learned, again, the more money you start with, the more opportunities to compound it, and the more you can leave it in there and not touch it, the more money you make. That's a good deal. All right. Let's do the same thing now with population change. So instead of Pert, now we're talking about Nert, right? So the population after a certain amount of time equals Nert. Now they use n sub 0. N sub 0 is just your initial population, just like before. Instead of money, we're talking about people now. R is our rate as a decimal, right? Just like with before. No different. T, time in years. Right? And N of T is our new population after T years. All right. So why can we use this formula? Why can we use E as the base? Well, populations are changing continuously. And since they're changing continuously, it's something that changes continuously, then we can actually use this Nert, all right? All right, and how could you use this to represent a decline in population? So sometimes cities lose people, all right? In this case, our rate would be a negative number, all right? We don't like it, but sometimes that happens, right? So let's try it. Let's go to 585. All right, we're going to do number 4 here together. All right, use the formula. For population, we will write a function of this model. All right, so the Fredericksburg, it has this much to start. That's our n sub o. And it has been continuously growing. Here's our rate. So, all right, so that's 0.029. All right, let's plug it in. So, n of t equals 1,900,360 e to the 0.029 t. T is the number of years. E is at 2.718, right? Like we got that. All right, so there's our formula. All right, so down here, we're going to predict the population in 2030. So from 2000 to 2030, that means our time is 30. So this is going to be 19,360 e to the 0.029 times 30. And let's do C as well, and then you can just calculate these numbers for you, all right? 19,360 e to the 0.029, and then 1980, that's actually going backwards. That's negative 20 years. Let's see what happens there. That's going to be interesting, all right? All right, and I want you to see if you can do 5. Estimate the population. You know, use your graphing calculator. See if you can find it somewhere in the table, all right? So pause the video and try those out. All right, so after 30 years, I found the population was 46,211 people. That makes sense. It's increasing. It's going up, all right, from 19 to 46. Down here, I'm going back in time. So from 1980 to 2000, it should go up. And it actually, that is true. It started in 1980 at 10,840, and it went to 19,360 people. So that does increase. It should make sense that this number is smaller because we were increasing as we went, and we went back in time. All right, let's see when it's 50,000 people. Now, I'm going to be honest with you. This is how I did all of it. Y equals, put my function in, went to my table, and 30 years, boom, 30 years. Same thing here. So how long it's going to take for over 50,000? It's going to take 33 years for there to be 30 or 50,000 people. All right. So there you have it. Let's look at our homework. Our bookwork is going to be page 591, numbers 1 and 2. All right. Not big, not a lot. Do your best. All right. All right. It's really important that you ask a lot of questions, ask for help, get anything you need to out of it. All right. And, keep on rocking. All right, till next time, dream big.